We are now going to start our study of probability distribution functions, and we'll end up starting with discrete probability distribution functions. But before we define a probability distribution function, we need to define a couple of other things. Our input variable in our probability distribution functions is known as a random variable. Random variable x represents a numerical value associated with each outcome of a probability experiment. So it's our input variable. That's essentially all you need to be concerned with. But we need to distinguish between discrete random variables and continuous random variables. The technical definition of a discrete random variable is that it has a finite or countable number of outcomes that can be listed. A random variable is continuous if it has an uncountable number of possible outcomes represented by an interval on the number line. So technically the notion of countable is fairly complicated mathematically. So I want to give you a basic understanding of what the difference is between discrete and continuous. And then we're going to analyze these two examples to see whether each one is discrete or continuous. I suggest asking yourself one question. Do all decimals between two numbers make sense? And you'll see what I mean when we look at the examples with this. If yes, then you're dealing with continuous data, or a continuous variable. If no, then you're just dealing with a discrete variable. So let's ask ourselves this question with each of these two examples. So the first one, the amount of time it takes to get to Lincroft campus. Is that a discrete or a continuous variable? Technically, it's continuous. Now, we of course say it takes 26 minutes, 27 minutes, 28 minutes, whatever it might be. But if you were to measure it accurately, it might be 26.38112858 minutes. We just don't measure that accurately when it comes to our commuting times. So technically, decimals do make sense here. Hence, this is a continuous variable. The second one, how about the number of students at Brookdale? Do decimals make sense in this scenario? Could we have 13,122.3811 students? That makes no sense. The only counting numbers are the number of students at Brookdale. Hence, this is a discrete variable. We're going to start our study of probability distribution functions specifically with discrete probability distributions. A discrete probability distribution is a function that assigns probabilities to each input of a random variable, but it must satisfy two conditions, and it has to satisfy both of them, not just one of them. It has to satisfy this one and this one. So what are these two conditions? What do they say? This is saying that P of x is between 0 and 1 for all values of the discrete random variable x. So all the probabilities, the outputs, all outputs must be between 0 and 1 inclusive. And the word inclusive here means that you're including 0 and 1. That's what that first condition is saying. The second condition says that sigma of P of x has to equal 1. Again, the capital Greek letter sigma represents a sum in mathematics. So this is saying the sum of the probabilities has to add up to 1. And notice it's not saying approximately 1, it has to equal 1 exactly. All outputs must add to 1. All outputs must add to exactly 1. Both of these conditions must be met, not just one. Both of them have to be met for it to be a probability distribution function. Let's take a look at an example. So say your probability experiment is to roll up one die, and let x, the random variable, be the outcome on the die. So 1, 2, 3, 4, 5, or 6 are the values that x could take on. And over here, I have a picture of the probability distribution function. Down here are the possible outcomes on the die, and then the corresponding output of the function are the likelihoods of each of these occurring. So the likelihood of getting a 1 is 1/6. The likelihood of getting a 2 is 1/6. The likelihood of getting a 3 is 1/6, etc. So this example is a uniform probability distribution function. But let's actually verify that both of these conditions are satisfied. Well, first, all the outputs have to be between 0 and 1. Since all the outputs have a value of 1/6, 1/6 is always between 0 and 1, hence that is satisfied. Also, we need all of the outputs to add up to 1. Well, we've got 6 bars here, each with an output of 1/6. 1/6 is exactly 1. So the outputs all add up to 1 as well. So both conditions are satisfied. Let us take a look at a couple of examples. Let's see if these functions, one here in numeric or tabular form and another here in graphical form, let's see if they could possibly represent discrete probability distribution functions. And remember, there's two conditions. You must have all p of x values be between 0 and 1 for all x, and the sum of the p of x's has to be exactly 1. Well, if we look at this first one here, the outputs, the p of x's, of course, I use the function name f in this case, they have to all be between 0 and 1. And in this case, they all are between 0 and 1. So that is satisfied. But also, the second condition needs to be satisfied as well. These should add up to exactly 1. 0.24 plus 0.1 is 0.34, plus 0.28 is 0.62, plus 0.3 is 0.92, 0.92 plus 0.09 is 1.01. So the sum of the f of x's is equal to 1.01, which is not 1. It has to be exactly 1, not something near 1. So that means that while this is a function, it cannot represent a discrete probability distribution function. Let's take a look at this one here and see if this could possibly represent a discrete probability distribution function. First, notice that the outputs of the function are 0.1, 0.2, 0.1, 0.3, and 0.3, all of which are between 0 and 1. So the first condition is met. The second condition is that they need to all add up to be exactly 1. Again, this was at a height of 0.1, 0.2, 0.1, 0.3, and 0.3. And if you add those all up, they add up to be exactly 1. So the sum of the p of x's is exactly 1, and all the p of x's are between 0 and 1. So this could represent a discrete probability distribution function. So this could represent a discrete probability distribution function. Now that we've established what a discrete probability distribution function is, people often want to know still, what is the mean of the discrete random variable? And to do that, we have a simple formula. And the mean of the discrete random variable is computed by taking the sum of the products of the x's with the p of x's, or the values of the random variable with the corresponding probabilities. Let's do this computation. I'm going to make a table here. We've got x's, we've got p of x's, and then we've got products of x times p of x's, and ultimately we then need the sum. So our inputs here are 1, 2, 3, 4, and 5. Those are the values of the random variable. 1, 2, 3, 4, 5. The corresponding probabilities, notice this is exactly the same discrete probability distribution function on the previous screen. And the likelihood of 1 occurring is 0.1. The likelihood of 2 occurring is 0.2. The likelihood of 3 occurring is 0.1. The likelihood of 4 occurring is 0.3, and the likelihood of 5 occurring is 0.3. So we need the products of all of these, and then we're going to take the sum of them. 1 times 0.1 is 0.1. 2 times 0.2 is 0.4. 3 times 0.1 is 0.3. 4 times 0.3 is 1.2. 5 times 0.3 is 1.5. And then if we take the sum of these, we have a total of 3.5. This means the mean value of the random variable is 3.5.